Welcome to our continuing series of discussions of the homework. I think this will probably be our very last one, second part of the Chapter 6 homework. And there's only one problem here that's going to be on the final that we'll need to skip, and that is 610 Part A. Some of 610 is pretty difficult to prove, but Part A isn't the hardest part there. So we are picking up at problem 6.8. So let me share the screen and we'll start talking through that problem. So 6.8 asks us to prove that on the log likelihood measure of degree of confirmation, if E is screened off, E sub 1 is screened off from E sub 2 by H on a probability function, then the degree to which E1 and E2 confirms H can be found by summing the degrees to which E1 and E2 each confirm H individually. So what we're looking for is we take the log measure on X, add it to the log measure on Y, and that's supposed to be the same as the log measure on what we get between the conjunction of E1 and E2 with respect to H. And he gives us a hint. Remember that when you sum logs, that's the log of the product. So we're just going to work with the log of the product and remind ourselves that by proving that the log of the product is the same as the conjunctive confirmation, we will have solved the problem because we can turn that back into an addition problem. It's just I'm not going to do that. I'm just going to prove the multiplication one and leave that last fact alone. So first, there's the log likelihood measure. The log likelihood measure on the degree of confirmation between E and H is the log of probability of E given H over the probability of E given not H. And to remind ourselves, the screening off assumption has three features. First, that E1 and E2 are relevant to each other. They're not actually independent of each other. And then the screening off assumptions themselves are B and C, that if you're given E2 and H, the probability of the same of E1 is the same on that as it is on H, and the same for E2 and not H and not H. Okay, so here's what we're trying to show. So we're going to try to show that the log of the product of those two things is the log of the probability of the conjunction given H over the conjunction given not H. And that takes advantage of the multiplication addition relationship on logs that he presented us as a hint. Now, for these two logs to be the same, we need the numbers that are generated to be the same. And so that's what we're going to try to do. 5, I just dropped the log remarks because we're going to show that those two values, the one on the left side and the one on the right, are actually the same. So here's what we're going to do first. We're going to turn this into an algebra problem because it just makes it easier to see what's going on. It gives you simpler variables to work with. The probability variables are pretty complicated. So what we're going to do is turn it into a straight algebra problem. And to do that, we're going to use the ratio formula throughout the entire problem so that we're going to turn every conditional probability into some ratio of unconditional probabilities by using the ratio formula. And then we're going to introduce 6 variables, X, Y, Z, U, V, and W, to stand for the following conjunctive probabilities. So X is going to be E1 and H, Y is going to be E2 and H, Z is going to be the conjunction of E1, E2, and H, U is going to be E1 and not H, V is going to be E2 and not H, and W is going to be E1 and E2 and not H, respectively. Okay, so we've got X, Y, Z, U, V, and W. So let's start with the left side of equation 5. all this stuff here, everything before the equal sign. And what we're going to do is take this first, let me get my annotator thing so that I can tell you what I'm doing. We're going to take this first probability and complicate it. We're going to complicate it by using conditions B and C from up above so that we can get both E1 and E2 into the numerator and the denominator here. Because we know we've got E1 and E2 over here. So if we're going to try to turn this thing into something that's provably identical to that thing, we're going to need to get one of these two to be more complicated. So we're going to pick the first one and make it more complicated than it currently is. Now remember, conditions B and C. I've now scrolled past them, but remember, if you have probability of E1 given H, that's the same as E1 given E2 and H. And E1 given not H is the same as E1 and E1 given E2 and not H. So basically, we're going to take the first part of the left side that uses E1 given H and E1 given not H and replace them with the more complicated sides of B and C in the numerator and denominator. Okay, so suppose we do that. Then here's what we get. And I'll just tell you which variables are in there, and you'll probably have to pause to verify that I did this, that what I'm writing down is actually what's there. So if you've got, the numerator is going to be Z over Y. So remember, Z is this conjunction. And Y is this conjunction. So in any case, we have Z over Y for the numerator on the first part, first multiplier in 5. And we have W over V as the denominator of the first multiplier. And then for the second multiplier, we have Y over the probability of H. And for the denominator, we have V over the probability of not H. And you can verify for yourself, just do standard algebraic reductions, and you get that that reduces to Z over W times the probability of not H over the probability of H. So that's going to be our left side of 5. Now let's move, let's move to the right side. I don't know if you know this, but I confuse right and left all the time. So let me fix that. Okay, we're back. Typo fixed, not typo, but confusing left and right. So we've finished the left side and found out what it's equivalent to, and now move to the right side. It is using the ratio formula, Z over the probability of H divided by W over the probability of not H. And as you'll be able to tell fairly quickly, this fraction reduces to precisely the same one that we had for the other side. So we have proved that the quantities are the same on both sides. Okay, on to problem 6.9. The Krupi-Tentori-Gonzalez measure. They think it's intuitive that whatever measure C correctly gauges conformation, the following constraint will be satisfied for cases of disconformation, but not conformation. So the conformation provided for H given E is the same as the conformation for E given not H when those are negative values, signaling disconformation. All right, so provide a real-world example of two propositions A and B such that intuitively A confirms B, but B does not confirm A to the same degree. And don't forget to specify which probability distribution you're using. Okay, Joe owns a red car, Joe owns a car. For this, pick any probability distribution you want. The probability of the second conditional on the first is going to be 1 because of the entailment condition. To get the second less than 1, assume there are exactly 2 colors, red and non-red, with equal chances. Then the probability of the first on the second is 0.5. Okay, so there's an example. Provide a real-world example of 2 propositions C and D such that intuitively C disconfirms D and D disconfirms C to the same degree. Don't make it too easy on yourself. Pick a C and D that aren't mutually exclusive. Okay, so the easy case is where they are mutually exclusive. A numbers being even disconfirms that it's odd, and the converse holds to the same degree. So that was the making it too easy on ourselves. How about this as a more interesting case? A fair die is tossed. It's coming up 1 to 3. Inclusive disconfirms that it came up 3 to 5 inclusive. The converse holds to the same degree. Does it seem to you intuitively that for any proposition C and D in probability distribution PR, if C disconfirms D, then D will disconfirm C to the same degree? Explain why or why not. No, I mean, this is just a discussion question. So that, no, it doesn't seem to me that that would be true. That sounds like it would be a very special case indeed. All the standard examples of throwing dice, drawing cards, urns, and the like are cases where it would be rare for the symmetry to hold. So the initial assumption of CT and G looks to me like an implausible starting point. The good thing is the measure that they provide is independent of that requirement. So their work can be significant even if it has an additional element that probably ought to be rejected. B, note, this one's fairly difficult. Yes, it is. So it's going to take a while to get through this. Prove that the L and Z measures never disagree on how strongly 2 pieces of evidence confirm the same hypothesis. That is, prove that there do not exist an H, an E1, an E2, and a probability distribution such that the log likelihood measure on H and E1 is greater than the log likelihood measure on H and E2, but reversed for Z on those 2 relationships. All right, now this is extremely hard to see your way through. So let me take you through the steps that I went through in thinking about what was going on here, because you have to get comfortable with the Z measure and how it relates to the log likelihood measure first. So let's just illustrate the pattern to expect in a series of values for the relevant variables. So I'm going to construct some tables and then we'll show what's going on in terms of the 2 measures. And maybe we'll start to see a pattern, and that'll help us see how to demonstrate the fact that we're supposed to be demonstrating. So the table we want is 1 for H, E1, and E2. So there's going to be 8 lines. And then you just pick some numbers for the probability for each of the state descriptions. Now, here on this, you'll be able to see this for yourself, but the log of H relevant to E1 is going to be 0.7 over 0.4, which is, of course, greater than the log of 0.6 over 0.4, but the Z inequality fails. The first line is the values, the second is the result. So for the Z measure, you'll have 0.35 over 0.55 minus 0.5 over 0.5. And that's not going to be less than 0.3 over 0.5 minus 0.5 over 0.5. So the L inequality goes one direction, and we can't, from this table, get the Z inequality to go the other direction, which is what we expected since we were asked to prove that they can't come apart. All right, so you're thinking, or I was thinking, let's see if we can change the assignment of values to the fourth column and try to give a counterexample to the claim we're trying to prove. So you can compare, if you wish, the probability distribution up here with down here. Notice I changed some of the values. So I gave some lines a little more value and some a little less, and I got the same result. So the L inequality is preserved going in one direction, but the Z inequality doesn't go in the other direction. So that one didn't work either. Now you can go through and inspect for yourselves by pausing the video to make sure that the numbers are as the table generates. If you see an error, let me know, but I think they're right. So, all right, so we've tried twice, and you can see raising the probability of not H over H made the failure a bit better. Let's reverse things to see what happens then. So notice what I did. The difference between the first table and the second table is that I gave more weight to not H than H, whereas in the first table, I gave them equal weights. Okay, so I weighted not H more strongly than H in the second table. So in the third table, let's see if raising the probability of not H over H, let's reverse. We first tried raising the probability of not H over H. Let's do the opposite. So now we have the probability of H being slightly higher than the probability of not H in this table. Now here, we still get the log likelihood inequality preserved, but once again, the Z inequality fails. And notice the failure is even bigger down here than it was in the previous table, which is interesting. So weighting H more heavily made things go even more strongly in favor of Z. So as expected, that should be made rather than makes things worse, either makes or made. So let's make not H significantly more probable than H to see what happens then. So now H is even more unlikely compared to not H than it was in the earlier table. So once again, the log likelihood inequality is preserved, but the Z inequality fails again. So that still was no help in trying to give a counterexample. One last idea is to try to get one of the second conditional probabilities to be lower than the probability for H, because we haven't done that yet. So try one more time, and one more time we get a failure. And this time we have a more interesting failure, because now on the one side, we get a positive number with the Z measure, and on the other side, we end up with a negative one. That's an instructive result. So if we want one conditional probability to be lower than the unconditional, we better do it for the first value. That's what the negative number showed us. So here, I've changed it again, and this time we finally preserved the Z inequality. We got the first number to be lower than the second, but the desired log likelihood inequality got reversed as well, which means this counterexample isn't going to work either. So the pattern is clear. Drive down the first value for the Z inequality, and you drive down the first value for the log likelihood inequality as well, undermining the disparity thing we were hoping to be able to show. So there is a pattern here about what happens when you drive down the first part of the Z inequality and uh, what effect that has on the first part of the log likelihood inequality. So let's begin with some key facts, starting with Z. Now I'm dropping the log function from the log likelihood measure, since the log inequality will track the inequality between the fractions that it's a function on. So first with the key facts, starting with Z. The probability of H given E1 is less than the probability of H given E2. And from L, we have the probability of E1 given not H is greater than or equal to the probability of E2 given not H. After cross-multiplying on the original formula of fractions for log likelihood, apply the definition of conditional probability, and we end up with this. The probability of E1 given H times the probability of E2 given not H is greater than the probability of E1 given not H times the probability of E2 given H. Then by reducing again, we get probability of E and H, E1 and H times the probability of E2 and not H is greater than the probability of E1 and not H times the probability of E2 and H. And from 2 and 3, it follows that the probability of E1 given H is going to be greater than the probability of E2 given H. So the probability of E1 and H is going to be greater than the probability of E2 and H. Now, suppose that the conditional probability of H given E1 is greater than or equal to the probability of H. Then the probability of, just replace this part with what you get by the ratio formula. That fraction is going to be greater than the probability of H. So the probability of E1 and H is going to be greater than the probability of H times the probability of E1. So from our assumption in Z, we derive that the probability of H given E2 is greater than the probability of H, allowing us to show that, oops, I have 7 here. This really ought to be 9. Probability of E2 and H is greater than the probability of H times the probability of E2. And the probability of E1 and H is less than the probability of E2 and H. But this contradicts 5a above. So we reject our assumption that the probability of H given E1 is greater than or equal to the probability of H. So we've now learned that the probability of H given E1 is less than the probability of H. As before, this gives us, that's not supposed to be there, 10, probability of E1 and H is less than the probability of H times the probability of E1. From this, we can divide both sides by H and apply the definition of conditional probability to get the probability of E1 given H is less than the probability of E1, which with 5 shows that the probability of E1 given H is less than the probability of E1, which is greater than the probability of E2 given H. If we apply the definition of conditional probability to 12 and divide everything by the probability of H, we get probability of E1 and H is less than the probability of E1 divided by the probability of H, which is greater than the probability of E2 and H, which entails that the probability of E1 and H is greater than the probability of E2 and H, which contradicts 5a. So on either of two contradictory assumptions, we generate a contradiction, which shows that our original assumption that there are values for H, E1, and E2 where the inequalities are reversed between L and Z is mistaken. There are no such values. Okay, that was long and tortuous. Let's move on to something that I hope is a little bit simpler. 611, we're now on to the Raven paradox. The solution to the paradox of the ravens is not the only subjective Bayesian solution that's been defended. An earlier solution invoked the following 4 conditions. Probability of a non-black raven is greater than 0, but the probability of a non-black thing is significantly greater than the probability of being a raven. So the probability of being non-black is greater than the probability of being a raven. So there's a lot more non-black things in the world than there are ravens. That's the assumption, which fits with our experience of the world. So the probability of A's being a raven given H is equal to the probability of A's being a raven. H is the hypothesis that all ravens are black. And the probability of A's being non-black given the hypothesis is the same as the probability of A's being non-black. All right, so both being a raven and being non-black are independent of the hypothesis. So assume that PR satisfies these conditions, complete each of the following. Prove that the probability of not R and not B is greater than the probability of RA and BA. Now I'm going to do a proof with a mistake in it, and I'm not going to point out the mistake, but I want you to look for the mistake and see if you see it as we go through the proof. It's a really simple and easy mistake to make, and then I'll explain why it's a mistake. But first, from lines 2, 3, and 4, plus the definition of conditional probability, we get that the probability of not B, A, and H divided by the probability of H is greater than the probability of A's being a raven and all ravens being black divided by the probability of all ravens being black. We can replace the numerators of these fractions with logical equivalents. So not BA and H is logically equivalent to not BA and H and RA, or not BA and H and not RA. And the same thing on the other side of the inequality, and we leave the denominator the same. So now we have the probability of a disjunction, and each of the disjuncts are exclusive of each other. Now, one of the disjuncts on each side has a probability of 0 because of what the content of H is. H is, remember, all ravens are black. Now, given H, if you have H as one of the conjuncts, you can't have all ravens are black and A is a raven and A isn't black. So this conjunction has a probability of 0, and this conjunction has a probability of 0. So what you're left with is the probability of non-black and non-raven and H over H is greater than the probability of raven and black over H. And conditions 3 and 4 above tell us that all of RA, BA, and H are independent of each other. Condition 3 and condition 4 are our independence conditions. So we can just multiply all of this stuff in the numerators. So the probability of not BA times the probability of H times the probability of not RA over probability of H is greater than the probability of RA and probability times, whoops, these should be times symbols rather than conjunctions, times probability of H times the probability of BA over the probability of H. Simplifying, that leaves us with the probability of not RA. So now I'm going back from the multiplication problem to the conjunction. So the probability of not RA and not BA is greater than the probability of RA and BA, which is just what we were supposed to prove. All right, now look at that. It's got a mistake in it. If you found the mistake, I'm fond of watching chess matches on YouTube, and there's a guy that shows classic games, and he always gives you a moment to pause and find the best move in the middle of the videos, and then he congratulates you if you found it. All right, so if you found the mistake, way to go. Where is it? It's right here. This is a mistake. Getting from line 3 to line 4, where, let me go fix those symbols so that you can see exactly, so there's no question of misunderstanding what happened between line 3 and line 4. All right, symbols fixed. Here's what we're looking at. Conditions 3 and 4, I said, tell us that RA, BA, and H are independent of each other. So you can take the formula we had at line 3 and just replace the conjunction sign with multiplication for each of the probabilities of the conjuncts. And then you get 4, and then simplify and replace the multiplication signs with conjunctions again, and we get what we were supposed to prove. All right, the mistake is moving from line 3 to line 4. I hope the mistake in the above is noticed. If not, look back at problem 3.9. 3.9 tells us that each of two things can be independent of a third without all of them being independent of each other. And that's what 3.9 was about. It was supposed to get us to consider whether or not you got complete independence just because you had pairwise independence. And conditions 3 and 4 only give us pairwise independence. So look back at problem 3.9 if you don't understand the mistake. So here's a quicker and actually easier proof than the above. Start with 2. 2 is the probability of not B is greater than the probability of RA. Not B, so I'm leaving off the reference to A. So the probability of not B is greater than the probability of R. And now we're going to replace not B with a logical equivalent of it. So not B is equivalent to not B and R, or not B and not R. And R is equivalent to R and B, or R and not B. Now the disjunction on each side of the inequality is exclusive, so we can simply add their respective probabilities. Then we subtract the common element from each side, and we're left with probability of not R and B is greater than the probability of R and B. The common element is this, the probability of that conjunction here and this conjunction here. So we're left with that conjunction on one side and that conjunction on the other. Okay, so it can be proven actually quicker and easier than the proof I used at the beginning that had a mistake in it. So that's nice. All right, prove that the probability of RA and BA and H is the same thing as the probability of H times the probability of RA. All right, so we know that the probability of H times the probability of RA is the same as the probability of H and RA. Forgot to put the A in there. And this conjunction is equivalent to itself plus BA, or itself plus not BA, the negation of BA. This disjunction is exclusive, so the right side of the equation is the sum of each, but the probability of HA and RA and not BA is 0, hence our formula follows. Okay, prove that the probability of not RA and not BA and H is the same as the probability of H times the probability of not BA. The proof strategy here is the same as for the last. Turn the right side into a conjunction, replacing the conjunction with its equivalent over the BA not BA partition. Turn the disjunction into an arithmetic sum and then delete the disjunction that has a probability of 0. All right, this one's a little bit more complicated, as you can see. The proof is going to take us on to 2 pages. So show that on confirmation measure D, if PR satisfies conditions 1 through 4 above, then RA and BA confirms H more strongly than not RA and not BA does. So this is what a Bayesian is hoping. When you find a black raven, that counts in favor of all ravens being black much more strongly than does a non-black non-raven. Okay, so we're being asked to show that on confirmation measure D, we get that result. So D looks at the difference between the conditional probability of the hypothesis given the evidence and the unconditional probability of the hypothesis. D is just the difference between those 2 numbers. So first, let's prove a formula for this difference letting E be a non-black non-raven. So the probability of H given E minus the probability of H is the probability of H times the probability of non-black given H divided by the probability of non-black over the probability of a non-raven given that it's non-black minus 1. Okay, that's what we're going to prove. So here's the proof of it. By Bayes' theorem, the probability of H given E is that the probability of E is the probability of a non-black non-raven, that's what we stipulated, which is the probability of non-raven given non-black times the probability of non-black, and 1, the probability of E given H equals the probability of non-black and non-raven given H, which equals the probability of non-raven given non-black and all ravens are black, times the probability of non-black given all ravens are black, which equals the probability of non-black given all ravens black, because the probability of a non-raven given all ravens are black and that A is non-black is 1. So the probability of H given E is this fraction, that over that, and the formula above follows from that. Now, the crucial middle part of this proof is right here in line 1. Where did we get that from? All right, here's a proof of that. So we start with the probability of A and B given C over the probability of B and C, B given C, I'm sorry. And that is probability of A and B and C over C times the probability of C divided by the probability of B and C, which equals the probability of A, B, and C over the probability of B and C, which equals probability of A given B and C. Now, I don't want to spend a lot of time on this part of the proof, but you may need to go very slowly through this proof. This is a fairly well-known proof in the literature. And so I have just copied it. I actually can't, off the top of my head, remember where I grabbed this proof from. I think it's one of the papers in the footnotes of the Titelbaum chapter, but I don't remember for sure. But once you see how this proof works, then we just need to apply the results of that for neg and positive to show that the latter is larger than the former. So the probability for the non-black neg is non-black non-raven, positive is black raven. So for neg, we multiply the probability of H times all the stuff about the non-black non-raven. And for the black raven, we multiply the probability times the stuff related to black ravens rather than non-black non-ravens. Now, by the independence assumptions, we know that, that the numerators of each formula are 1. Since multiplication doesn't alter comparative size, let's factor out the probability of H for each formula. Then we hope to show that 1 over the probability of black raven minus 1 is greater than 1 over the probability of non-black non-raven minus 1. We have shown above that the right denominator is larger than the left, so it follows that the left value is larger than the right, because they're both going to have negative values. Yes, and I didn't, I paused there because, as you know, I mess up left and right, but this time I did not. I was careful and didn't do it. So where in your proofs did you use condition 1? The proof above assumes that the probability of E times the probability of H times the probability of not B and H is greater than 0. So that's going to require condition 1 in order for that fact to hold. Finally, suppose PR is your credence distribution when you know you are about to observe an object A drawn from the hall of atypically colored birds. Which of conditions 1 through 4 will PR probably not satisfy? Well, go read about the hall of atypically colored birds. The independence condition 3 won't hold, since given the hypothesis, there'll be no ravens in the hall.